Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome back to another NL Math Man Math Help stream. We're here on day 55. Boy, 55th stream. The 55th Math Help stream that I've done. Boy, we're really getting up there, aren't we? We're at sort of like the middle end, you know what I mean? Like it's not quite the finale yet, right? But it's like those that last few episodes, like before it gets on to the end ones. Like maybe we're not quite into like the resurgence of continuity. Maybe we're still doing like Monster of the Week episodes, right? Like if it's a Doctor Who or an X Files or something like that. Like we haven't quite reached back to the point where we're into the season arc yet. So we're still like this is just like a one shot, right? This is just gonna it's just gonna come and go. We're just gonna the Cybermen are gonna show up for like one episode or whatever. Like then they'll leave again though, right? They won't actually be part of the finale. Maybe they'll just pop in and pop out. Maybe we'll have the farting aliens again, right? That's a deep cut. It's a deep cut for that's the kind of stuff in Doctor Who we don't like to talk about, right? I mean, real talk, real talk. Like it's really hard to introduce people to Doctor Who through the Chris Eccleston episodes, right? Because you've got some real humps to get over. Like right away, like with the like the trash bins, the plastic aliens, that's okay. Like it's not bad, but then it gets straight into like the obese farting aliens like crammed into these like bodies that don't fit or whatever, and it's just boy oh boy, it's a real bump to try to get over to get people through. So I say just start them on the empty child. Just start them right in the middle of it. Just slam them right in there. Get them in that in like one of the most terrifying the abject horror of the empty child episodes of the first season of Doctor Who. Get them in those, and then get them to move on, right? And that was a Chris Moffat episode anyway, right? So those ones are written and directed by the next showrunner, who would be the showrunner with Matt Smith, which was some great episodes. I don't know. I'm talking like I'm some kind of Doctor Who expert here, but I haven't seen any of the Peter Capaldi episodes, right? Not a single one. But Peter Capaldi was amazing in Torchwood season three, right? Children of Earth, but like Torchwood season three is that's a real gem. That's a real gem of sci-fi TV. Like that is up there. That's one of the best around. Anyway, that was a good digression. Boy, that was a bit of a fun one. I thought I was going to be a bit down in the mouth here today on stream, but no, I got off onto talking about sci-fi TV shows, and you can have a solid 2 minutes of fun there. But yes, it is. We are sort of like at the middle end here now, right? We're not quite into the finale episodes, like I was saying. That'll be next week, I guess, right? Because you know we do have an end date for the semester, for the stream, and for my employment, right? So June 26th, I'm unemployed. Look at that. Look at that. You know, you put in you put in the time to make the stream and stuff like this, and then yeah, see you later. Anyway, we're gonna we're gonna make the best of the situation. Maybe I'll do some of that hiking like I talked about. Anyway, we're yeah, I'm gonna cut the banter a bit short here today. We do have a nice picture of doggies in the background, right? But I got loads of those. Flurry is looking very photogenic in this picture, though you can't quite see her heterochromia as well as in yesterday's picture. But this is an action shot, right? Or at least a gentle action. They're on a casual trot back to the cabin, I suppose, through a skidoo track. Anyway, today, like I said, I'm not going to spend a ton of time on the right. Am I even coming in from? Oh yes, I am. Okay. I don't know why. Like ever since episode two, I've been really paranoid, looking down at my mic levels and like, am I even coming through? Like, what's going on? Anyway, we're gonna start off here with histograms today. So, Betty Ann, that'll be for a course that you were doing. Just a few quick rules about them. Um, yeah, they're not an incredibly important topic. Well, they are, but they're not for our program because it's not going to come back up. Um, yeah, there's just a few basic rules. Intro to Pythagorean theorem. I have done sort of an angle on that before, but Renata, that'll be for your course. And afterwards, I will link you this part and a previous video as well that I did a different type of intro. I did like Math is Fun, the website, and I talked about like the actual reasoning behind the Pythagorean theorem. So I'm going to skip a bit of that today. Um, I'll take a bit of a different angle at it, and then I'll do some word problems. Counting principal word problems, Calais, that is for your review sheet. Excuse me. Boy, I'm phlegmy. That's for your review sheet that you just did. Um, yeah, it's just word problems on the same topic we've been working on. Then if I have enough time, I'm going to get to volume of regular shapes. Currently, we'll need that topic soon, although perhaps not for tomorrow. So we'll see how close we are to the hour and a half by the time I get to that point. Okay, so first up, like I said, I'm going to go on over to this display. We're going to talk a little bit about histograms, right? So a histogram kind of looks like a bar chart, but it's not really a bar chart at all. A histogram is for continuous data generally. Well, not necessarily continuous as in discrete versus continuous, but it shows sort of an amount of data over. Well, it's on. I'm sort of fumbling with my words here, but as you can see over on the side, right? So it basically shows how many entries there are in each of these bins. Is really what I'm trying to say. What I'm trying to squeeze out one way or another, right? And what are the main points when we're choosing how we're going to draw our histogram like this? Well, we have to choose the size of the bins, right? And then we have to choose basically what categories each of our data points fall into, right? Now, I know here it says this is the introduction to histograms in this course. It says choose a suitable bin width. Now, like what does that mean? What does suitable bin width mean? That's a bit like, that's a bit like starting off saying, well, the way you get the question right is just you get the question right. Come on, like forehead, right? Um, to Twitch meme there. This is odd, right? It's a Twitch channel where I can make a Twitch meme like that, and like nobody that watches me would get that one. Just get it right, forehead. Anyway, this is Math 2101B. Unit, what is this? Unit 2? It doesn't really matter. Yes, Unit 2. Okay. Okay. So when choosing histogram bins, we should make sure to have enough bins to visually represent the spread of our data. Usually 5 to 10 bins will work, right? So we want to make sure that in the data points that we're representing, we have, let's say, here it says, they choose 6 down in this one. I mean, generally I would choose maybe even more than 6 for a histogram, but for our purposes here, 5 to 10 should work because we want enough bins to represent sort of the spread of the data really well. Because ideally, right? So for example, say we had the normal distribution, right? Say we had roughly, here we go. That's roughly a normal distribution there. If we only chose to split this like into, well, okay, I should, before I get onto this, I should mention another point. Um, So we don't need to include leading or following empty bins as well, right? So if your data starts at 16, right, you don't need to have empty bins from 0 up to 16. You can just start your histogram on the bottom axis at 16. That's totally fine. I'll show you in a bit that we use sort of a jagged line, sort of like a lightning bolt looking thing, to indicate that you skip some points on one of the axes. But it's totally fine. Like you don't need to have empty bins, right? But for example, take this normal distribution, or this rough normal distribution here. Imagine if we took that and split it into, I don't know, split it into 3 bins, right? So let's say we went from here on over to here, like that, right? And if we split it into 3 bins, we might have, say, you know, um, 1 bin here, 1 bin here. Now imagine these were more accurately drawn, right? So if we had, say, 3 bins, right? And back can't get rid of me that easily, Kappa. There we go. That's what I was just talking about Twitch memes. See, Kappa's an immortal one. There we go. That's a good one. Welcome back, Slayer Darth. So with 3 bins, we don't get a good representation of our actual data, right? Like, I know what I'm doing here is off a bit because I'm doing all this freehand, but you're seeing what I mean, right? Like, we get a very, very, very rough example of what the normal distribution is, right? But we're really not getting a good example here because, say, look at this leftmost bin, right? We know from looking at our actual curve, the line in black, that over here to the left, there should be basically nothing out here, and then a fair bit here, and then more over here, right? But if we take it and average the whole thing over this whole section, well, this bin might be relatively accurate in the sense that, it does represent how many values are between this point and this point. But it's a bit disingenuous, meaning it shows less information than what we actually know, because we actually know that the data is clumped more over to this side, right? And there's actually quite a bit over here, but basically nothing over here. So because we've chosen so few bins, our representation is actually, it's skewed quite a bit. But to say we were to take this now and do a lot more bins, let's say I was to double the number of bins, maybe to 6, maybe even we'll go. Now we'll do 6. So we'll do roughly half of these guys. Right? So I'm basically saying, with 6 bins, right? With 6 bins, we get a closer representation to the spread of our data. And of course, this is going to continue. Like, say I was to split these again in half and do 12 bins or something like that. The more bins that I have, the closer it's going to get to the actual spread. Now, the point of a histogram in general is because we don't tend to have the information that we have here, right? So this black curve that I've drawn, that, assumedly is the exact, right? That's the exact spread of our data. And most of the time when we have a situation like this, we don't have that information. What we're given is all the different data points, right? So a histogram exists in order to sort of show us a bit of the spread of our data, knowing that, it's not going to accurately fit a curve necessarily. But the more bins we have, of course, generally the better it's going to match the data, match the spread of our data. Now, the point of it, of course, is to take all the information that we have in all these points, right, and then condense it down into a different form, right? If we did, like, here we have what, 5 times. So we have 40 points here. If we did a 40 bin histogram, right, like, it's going to be basically no different than just graphing all those points and drawing a line and joining them up, which I guess we could do, right? We could do a quadratic regression or some other sort of regression. It probably wouldn't be quadratic, but either way, we could do a regression to find a line that matches all these guys. But the point is that in actual statistical analysis, right, we would have such large groups of numbers that classifying them into a histogram like this is extremely useful. We do still want to have more bins, though, because more bins gets us a better representation of our data. Oh, right, there was one other rule. Yes, there was one other rule I wanted to mention here as well. So I'm going to include it on this sheet as well, just because, Betty Ann, I'm just going to send you this one as part of the notes. Our histogram bins include the lower limit, but not the upper limit, right? So sometimes we may write a bin as, say, I don't know, 36 to 40. It's actually 36 to less than 40. Right? So this is another point as well that it's important to know, and it does make sense. Like when you look at a graph like this, right? If this was, say, 0 to 4, imagine if it was exactly 0. Well, it would go in this one here. But if it was exactly 4, it's actually going to go in this one. Even though this is written as 0 and this is written as 4, and this may be written as 8 and this is 12 and so on, right? The actual value 4 is not directly here on the line. It's actually in this one, right? So it is really important to know this other rule as well. And this is one that I don't think your notes mention this explicitly, right? But it really needs to. Oh, no, it does say, choose a frequency table. The number 10.0 is recorded in the 10 to 15 bin. Sure, it's right there. It's right there on the piece of paper that I'm looking at, right? It's right here. Now, it doesn't explicitly say what that means, but you could follow through the logic, right? So if 10 is included in the 10 to 15, well, then 15 is going to be included in the 15 to 20, right? It doesn't out and out say that, but that's what it means. So the 10 to 15 bin actually isn't really 10 to 15. It's 10 to less than 15, right? So 14.99999, that goes in that bin. 15.0 doesn't. So I'm going to pop over to the assignment here, or the worksheet rather, right? So this one asks us to draw a histogram, right? And I'm going to go down through now. I'm going to draw this one, draw something out really quickly here for this histogram. Now, like I said, we don't need to incorporate any leading empty bins. So whatever our lowest number is, we can just start with that one. We don't need to mess around with having well, they did do a leading empty bin on this one here, so maybe this is a poor example, but you don't need to do that, right? They could have just done the lightning bolt thing, the little jagged line, and then started here at 5 over on the corner and saved themselves some space, right? So here now, let's see, what is our lowest value? Our lowest value in this list appears to be, what, 5.6? Yes, 5.6 it is. So I'm going to start with, let's say, 5.5 to 6, 6 to 6.5, 6.5 to 7, 7.5 to 8, 8.5 to 9. Oh, sorry, 8 to 8.5. My goodness. 8 to 8.5, 8.5 to 9, 9 to 9.5. Oh, see? My God, I already messed it up. I already messed it up. You see, I'm trying to pay attention to too many things at once here, Twitch chat, and I already messed it up. Okay, so you know what I'm going to do? I'm going to go print off another copy. Hold on. It is Like, I shouldn't be doing math in pen. Why am I here doing the math in pen? I'm supposed to be the teacher. Oh boy, oh boy. What question is this? Yes, this one here. All right. It's tough, you know. It's tough. It's tough to write out numbers, just like write one number after another and get it right. Boy, oh boy, that is difficult, right? I'm just writing down numbers. Here we go. The printer barfs another sheet straight into the trash bin. There we go. Just wasting a bit of ink here in front of y'all. It's good. It's good content, right? Okay. So again, an S and then a more different S. This is another strong bad email reference. He just doesn't stop with those. 7 to 7.5, 7.5 to 8, 8 to 8.5, 8.5 to 9, 9 to 9.5, 9.5 to 10. Right? I don't think we have any 10s on here, so we should be good. All right. This time we got there. We did it. We did it, Reddit. We managed to do it. Okay. So let's go through and now count up the number that's going to go in each of these bins. Well, here's one for the first bin. Looks like it's it. Tally 1, frequency, more different one. Okay, 6 to 6.5. Let's see, we've got 6.3. Is that it? Is it again? Boy, okay. One there. 6.5 to 7. There's one. There's two. I should be putting the tallies down in there instead of just trying to remember it. That looks to be it again for that one. 7 to 7.5. Well, there's 1, 2, 2 again. 2 again. 7.5 to 8. 1, 2 there. 3 there. 8.0. Does that go in this one? Nope. No, it don't. No, it do not. There's a 7.9. What else do we have? Oh, there's a 5.8. There was a 5.8. There we go. Make it 2 up there. Right? We got there. There was a 5.8, chat. 7.5 to 8. 7.5 to 8 looks done. Okay. 4. 8 to 8.5. Let's see. So there's going to be an 8.0, another 8.0, an 8.3, an 8.2, another 8.2. Yep, seems good. 8.5 to 9. 1, 2, 3, 4. Is it 4? Yep. 9 to 9.5. There's 1, 2, 3, 4, 5, 6. And 9.5 to 10. 1, 2. Okay. So now I'm going to go through and I'm going to draw out my histogram. So now that I have this frequency table done, now I know, well, I know what my bin sizes are. Those are going to go down bottom here. And then I also know what frequency I have to be able to get up to on the max. So I only need to be able to get up to 5. So this size chart is going to be totally fine, right? So what are we looking at? The results. So the results are this way, and then the frequency, we should always label our axes. Frequency is this way. like so. Okay, and now we're going to start off with 5.5. So I'm going to do, let's see, yeah, so let's do 6 there, 7 there, 8 there, 9 there, and then 10 over here, right? So then it's going to be obviously 6.5, 5.5, 7.5, 8.5, and 9.5. There, sort of all across the bottom like so. All right, so now I'm going to go ahead and draw in my histogram. So for my first, now like I said before, right, you don't need to start with empty ones, but this having this blank here does give me a good opportunity to show you the notation that we use, right? So if I zoom in a little bit rid of mo, zoom in and rid of mo, we're going to see that this is what I do, right? And it's this symbol here, that tells us that we skipped some, right? So because we're not starting at 0 on this side, I'm going to go and skip that many and put it in like so, right? And then I'm going to have 1, 2, 3, 4, 5, and 6 over here. So I'm going to skip, I'm going to use 2 blocks to represent 1 basically. So then 5.5 to 6, well, that's going to be 2, here like so. 6 to 6.5 is 1, so we're going to come down a bit and go over there like so. 6.5 to 7 is 2 again. 7 to 7.5 is also 2. 7.5 to 8 is 4. I'm sliding my sheet all over the place. 7.5 to 8 is 4 like that. 8 to 8.5 is 5. 8.5 to 9 is going to be 4. 9 to 9.5 is 6. And then 9.5 to 10 is 2. All right, and there we have it. All right, so I know that took a little bit of time to do that one out, but this is now the histogram showing the Canadian figure skating team's results, right? So this is basically how it should look. And one reason why this is a decent histogram for this situation is because it does show off sort of the spread of our data relatively well, right? Without necessarily listing off every point, it kind of shows us that the team was definitely clumped around here, but that there was some sort of variance as it was going. This is definitely not a normal distribution, right? But the thing is, right, perhaps it is tending toward a normal distribution, right, with the center being here and then there being more outliers in this way. But of course, a value that has a hard cap, like has a cap of 10, obviously can't be 100% normally distributed, right? Because unless they're grading on a curve, as they say, such that there is only ever 3% A's in the whole group, right? So that means there should be only 3% of people above 9 if they were actually grading on a curve, and then the bump should be here in the middle, right? Anyway, I don't, like I said before, I don't want to get into the pedagogy of grading on a curve versus not, but it's an all too common thing that people tend to seem to think for some reason is a proper thing to do, right? It boggles the mind. It's seems to be a misunderstanding of the math involved. Anyway, right? The part that confuses me is someone who can understand normal distribution well enough to even be able to explain what grading on a curve means, and then at the same time not understand why it's a problem to grade on a curve. But anyway, introduction to Pythagorean theorem. Yes, I do want to do a little bit on that topic. So let's Introduction to Pythagorean Theorem. That is going to be over here, yes. Okay. So let's skip on back over to the document display. Renetta, this is the guide that you will be looking at to start off with your Pythagorean Theorem section. Like I said, I will link you to another video as well that did mention sort of a different take on doing Pythagorean Theorem. But I'm going to look at your book for a second, and let's go over. Well, these are the questions that I'm gonna go down through eventually, or shortly. But I'm actually going to go down through this exploring the Pythagorean relationship thing. The center of a piece of centimeter grid paper. Draw a right triangle with legs 3 centimeters and 4 centimeters. Well, let's go and actually do that. Hey, why not? Why not? Let's do that. Right? So this paper here is not quite centimeter grid paper. I don't believe. Let's find out. Let's find out if it's a centimeter. No, these are half centimeter grids. Okay. Or 6 millimeter, actually. Odd. Oh, it must be done by inches, I guess. Yes. It's probably an accurate number of eighths of inches. Yeah, so tell you what, I'm going to, instead of doing what it shows there, exactly, I'm going to take this stencil here. I'm going to take my, this stencil that I've been using all along, and I'm just going to outline it. We're just going to outline this guy, and that's going to make us a right triangle. Okay, this one's getting a little bit big. It's a bit big for the activity that we're doing, but it's going to be fine. It's going to be totally fine. So, I know, because of the Pythagorean theorem, that I can use this side and this side to figure out what the length of that side is over there, right? Because, let's see, let's measure this side here. Now, it's going to be a little bit tricky because my ruler is not quite long enough. That's going to be 10 there plus 12.6, right? So it's going to be wait, what? 10 there plus 2.6, yes. So 12.6, yes. So this is 12.6 centimeters on this side, right? This one over here, let's see, let me get this a bit more accurately. This one over here is going to be about 70, I'm going to say it's 74 millimeters, so 7.4 centimeters on that side. Right? So based on this information, I can actually go ahead and figure out what this length of the triangle is going to be over here. Right? So I know that if I was to take this side and square it, right, because this is a right angle, if I was to take this one and square it, so 12.6 squared, and then add that to this one, 7.4 squared, that's going to equal the same as this unknown one here squared, which I'm going to call C, right? Because we know that the Pythagorean theorem is a squared plus b squared equals c squared, right? And what your book is showing you over here, well, I'll get to that in a second. Actually, I'll get to that more accurately there now in a quick second. But first, I'm just going to show you that the formula works. 12.6 squared, and it works even in real world situations, because this is not a example from the textbook, right? I literally just drew this triangle by tracing the ruler that I'm using. 54.76 equals c squared. So I'm going to take those two and add them together. 158.76. It's going to be 213.52 equals c squared. Now I have to take the square root of that. Right, and zoomed in a bit far. Oh, come on. There we go. Square root of that answer. It's going to be 14.6 equals c. So now if I was to take this ruler and measure this, I'm expecting to get about 14.6. Now it would be exact, but as you notice, the corners are rounded, so measuring that is a bit tricky. And also this was rounded a little bit at the end here. But let's go through and find out. Let's go through and see. It's going to be 10 there. And that's going to be 4.6. Look at that. Another 4.6 there. It is indeed 14.6 centimeters. That was exactly right. Oh my God. How did Pythagoras do that? It's a good question. How indeed? Well, the observation that he made was that a squared plus b squared equals c squared, right? So if I was to draw out an even a smaller one like this, right? If I take a square where both sides are the length of this side and a square where both sides are the length of that side, that's going to add together to make a square where both sides are the length of this one, right? So if I was to draw that, let's go ahead and draw it over here based on this one, so this is about 2.1 centimeters. So another 2.1 centimeters. I'm going to draw that across here like so. 2.1, another about 2.1, and then join that guy up. Right? So that's going to be 2.1 squared, which is going to be about 4.4. So this is about 4.4 centimeters squared, right? Because this is 2.1 cm. Then over here, if I was to measure this other side, this one is going to be, it's about call that about 3.6. So that's 3.6 centimeters. This side over here then, once I draw this one out, oh, I'll use a different color. So over here then, the red one, 3.6 squared, it's going to be 12.96, right? So now I know what the area over here is going to be of this last one, right? Because I know the area of this last one, once I draw that, is going to be this one plus this one put together, right? But let me just go ahead and show what that's going to be. It's going to be, it's about 42 millimeters or 4.2 centimeters. So let's go ahead and draw out that. Join that up. So then 4.2 squared. It's about 17.6. Okay. Well, I was obviously a little bit off. I was a little bit off with my measurements at some point on this one, but that's to be expected. I was only a tiny bit off though. It should be 17.4, right? And I was probably just a little bit off on one of these measures. But as we see there, that's pretty close, right? To get even with just grabbing a ruler and just measuring it like that, to get within, 0.2 of the answer is pretty good. But what we know there now is that right? So a squared plus b squared equals, let me just keep on going through, equals c squared, which means, right, which tells us blue square plus red square equals green square. Here, right? And that's really what the Pythagorean theorem is that when we have a right triangle like this, right? The blue square, or this side squared, plus this side squared equals that side squared. Right? And this is the way that it's written out. So, like I said, I'm going to use that then to go ahead and answer these ones. Just I have a text from to deal with some stuff from other students. So generally, I don't pause the stream to do this kind of stuff, but just give me a quick second there, Twitch. I don't believe there's anything super pressing going on in chat right now. So yes, just let's just hang on a second. Okay, sorry about that. I don't think that was that was probably not a big deal. Chat isn't it wasn't popping off in the meantime. My moderation team has got it all handled, right? We're keeping it on lockdown here. All right. So this is going to be math. Um, Geez, what am I doing? Math 1102C, Unit 1. And I'm going to do these ones. This is page 297? Yes. Page 297, I'm going to do numbers 5 and 6. So we're going to do a few word problems. Question 5. So a ramp from a walkway to a doorway has a height of 30 centimeters. The length along the ground is 4.5 meters. Calculate the distance a wheelchair travels along the ramp. Write your answer to the nearest hundredth of a meter. Now, this is a really good question. I say that a lot. I know. It's a really good question because it's very similar to one you're going to see on your test. Nudge, nudge, wink, wink, say no more. Right? But one reason why this is such a good question is because it's got two types of units combined together. So you have an extra step at the beginning that you need to be able to do. The step at the beginning you need to do is convert all your measurements to the same unit, right? So if we have 4.5 m and 30 cm, well, we need to do one or the other. Apologies, Renata, for this pause in the video. I'm going to need to pay attention to this thing again here. Boy, it's just like they say, right? I mean, like I stream for like an hour and a half a day every day, and I mean, when do you get the urgent text messages and the stuff, right? I got to tell you. Okay, no, we're still here. Okay, I didn't turn the mic off that time. All right. So first we need to convert to have the same units, right? So we're either going to need to convert the 4.5 meters to being centimeters, or we're going to have to convert the 30 centimeters into being meters, one of the two, right? So I'm going to do 30 cm multiplied by, remember now, this is unit conversions. This is stuff from a previous unit, but it keeps coming back up, right? There's going to be 1 meter per 100 centimeters. That's our conversion factor. So then the centimeters are going to cancel with that. We're going to have 30 over 100 meters, or 0.3 meters, right? So now we know that the two measures are 4.5 meters this way, 0.3 meters this way. Okay? And now we can go ahead and do our a squared plus b squared equals c squared, our Pythagorean theorem. Right? So then we're going to have, so a squared is going to be 4.5. We're going to square that one. B is going to be 0.3. That one's going to be squared. And that's going to equal c, or the hypotenuse, which is going to be this one over here. Right? Now we're going to have to break out the calculator. 4.5 squared, 20.25. 0.3 squared is going to be 0.09. 4.51 equals C, right? So write your answer to the nearest hundredth of a meter, right? And then it says first change 30 centimeters to meters, right? It's written right there. It's written right there on the question, isn't it? So the answer is 4.51 meters. The ramp is 4.51 meters long. Right? So again, Renata, like I said, these examples might be a little more advanced than the very basic sort of beginning ones, but I am sending you a link as well with some initial ones at the beginning in it. And now these word problems are going to be quite useful for you as well. Right? So question 6, in softball, the bases are often set 65 feet apart in the shape of a square. The catcher throws a ball from home plate to second base. How far is the catcher's throw? Round your answers to the nearest foot. All right. So we know that the baseball diamond is going to look something like this. Now mine's not going to be really not going to be a very good diamond per se, but it doesn't matter. Like I say, for these diagrams, right? What matters is what's written on them. Okay, so the bases are set 65 feet apart in the shape of a square. So we know that this is home plate down here, right? And this is first, second, and third base. And we know that they're set 65 feet apart. So this is 65 feet here. This is 65 feet here. This is 65, and so is this one. Right? What we're asked to find then is going to be this green line that I draw here, right? Because it says the catcher throws a ball from home plate, which is down here, to second base, which is up here. So of course he doesn't, he throws it direct in this length here, right? So then we have to find out how far that is. This is the right angle here, right? We know that that's a right angle. So we know that our Pythagorean theorem, right, is a squared plus b squared equals c squared. And c always has to be the hypotenuse, right? C has to be the side that's opposite the right angle, here like this. So the other two sides are going to be 65. So here we're going to have 65 plus 65 squared plus 65 squared equals c squared. So 65 squared is 4,225. So this is 8,450. So that's 91.9. Round your answer to the nearest foot. So catcher's throw is about 92 feet. There we go. All right. So that is a good intro then, I think, to some of the questions, Renetta, that you will be doing in this unit. Back over to my intro screen here. So, counting principal word problems. Okay. All right, factorials, NPR and NCR. Okay, quite a few to go through for these ones. So let's see here. There's 8 to 13. All right. No, let's use this. Let's keep using this display today. But how about I change the background a bit? There we go. Let's go back to that one. Okay. So from standard deck of 52 cards, how many different 5-card hands are there with at least 4 black cards? There we go. Okay, we're getting it all on the screen here now. So at least 4 black cards. It's going to be, we can either get 4 black cards or we can get 5 black cards. So it's going to be Math 3101A, Unit 2. All right, so this is going to be the review sheet. Start off with question 8. So at least 4. So in this case, it's going to be 4 or 5 black cards, right? So standard deck of 52 cards, how many different 5-card hands with at least 4 black cards? So we know that the hand is 5 cards, right? And we know that the order doesn't matter, because whether you're dealt, whether you're dealt the cards first, second, third, fourth, or fifth, it doesn't matter. It's still going to be the same card. Like I mentioned before, you can rearrange them in your hand all you want. So we know we're going to be using combinations, or C, not permutations, or P, right? So then at least 4. So there's 26 black cards in total, right? Because half the deck is black. So there's going to be 26C4. And then along with this 26C4, right, because this is 4 black cards, we also need 26C1. Because at the same time, which is an and, which means multiply, we need to have 1 red card in order to make our full 5. Now there's an or, because an or means another situation that also fulfills the requirements that we have, right? And then the other situation that fulfills the requirements that we have is going to be 5 black cards, 26C5, and then 0 and 0 red cards, 26C0. Now, the 0 is not super important because we know that anything C0 is 1. Right? We have 26 items. How can we choose 0 of them? We'll tell you what, just one way. Just don't pick any of them. There you go, you're done. That's the only way to do it. There's one way. Right? Like, it just makes sense, doesn't it? Done it? All right, so 26C4 is going to be 26 factorial over 4 factorial 22 factorial. Then 26C1 is going to be 26 over 1 factorial 25, 52, 25 factorial. Then we're going to be adding 26 factorial over 5 factorial 21 factorial times 26 factorial over 0 factorial 26 factorial. Now, I'm saying the word factorial a lot, just like I always do when I'm reading these guys out. But now we're going to go through and be able to cancel some of these, right? So this is going to be 26 times 25 times 24 times 23 over 4 times 3 times 2. And that's going to be multiplied by 26 over 1, right? Or just multiplied by 26. And then we're going to be adding 26 times 25 times 24 23 times 22 over 5 times 4 times 3 times 2. Oh, this pen's starting to run out. Look at that. And then that one is going to be multiplied by 1. Just a 1. It's a straight up 1. 26 factorial over 26 factorial is just going to be 1. So that's not actually going to do anything at all, of course. Right? 26 times 25 times 24 times 23. Divide by 4 times 3 times 2. Divide by 24. Yep. There we go. 14,950. That's going to be still multiplied by our 26. Then we're going to be adding in our 26 times 25 times 24 times 23 times 22. Divide by, well, I know that 5 factorial is 120. Plus 65780. That's going to be 14,950 times 26 plus 65780. $454,480. Okay, there we go. So that is the number of ways in 8 to make, that's the number of different 5-card hands that can be made with at least 4 black cards, right? Because this case over here was the 4 black card and also the 1 red card, or 5 black cards and 0 red cards. Right? So those are the 2 situations that satisfy the instance that we have, or the requirements that we have, rather. Right, I'm going to skip 9, because 9 is just one that you can just plug in your calculator, kind of. I mean, right, if you can do these, right, this here is just the same as 9. This is just 8. That's, I guess, the point of 9 is seeing if you understand that other notation, but all that is 8C5. All right, so I'm not going to go through and do that one right now. Number 10, the mall is 3 blocks east and 2 blocks south from Mandy's house. How many routes can Mandy take from her home to the mall? Da mall. Right? Well, we know that Mandy needs to travel 5 blocks in total, basically, right? Because she needs to travel a total of 3 east and 2 south one way or another. Right? So we know that, I'll write this out in words. So Mandy has to travel 3 east and 2 s in total. So 5 blocks. Right? So we know that in some combination, she needs to go east, 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 south, south, like that. So basically, this is now just one of those questions about rearranging words, right? But instead of a word like Saskatoon or something like that, or, I don't know, Burnaby or Victoria or London or Ottawa, right? Or Waterloo. Instead of those, right? Or Quebec City. I don't know. Anyway, instead of any of those place names, we just have this word east, right? Eeess. Just imagine that was a word, right? I mean, it's almost C's, Sees with an E on the end, right? ECs. ECs. There we go. It's like someone sees something electronically. He sees it. Yeah, so it's an anagram. Uh, this is good. This is great content. This is the gold stuff, man. Come on. This is what the viewers tune in for, right? Yeah. Um, but what we have here now is just five elements, right? Three of which are the same, and two of which are the same. That's it. That's all you got to do, right? Once you see it written out like this, I think it makes a lot more sense compared to what we've done so far, right? Because what we have over here, with this grid, you're like, well, how many ways can she go? Well, she can go this way, this way, this way, this way, this way. She can go this way, this way, this way, this way, this way. I mean, she could go like this. But we're not counting that, right? We're not counting her like doubling back and going north because she, saw somebody she knew that she didn't want to talk to and she just turned and ran the opposite direction or something, right? We're not considering that sort of nonsense. All we're going to do is assume that she goes directly there some way, which means there's three east and two south. So it's five elements, three are the same, two are the same. So that just breaks down then into 5 times 4 over 2, right? Which is just going to be 20 over 2, which is just going to be a big fat 10 ways. That's it, right? She just has 10 ways to get there. Provided that she goes direct, of course, like I said. Provided she doesn't, like, see Janie that she doesn't want to talk to, and she's like, gonna have to bounce. gonna have to go back north for a bit, right? Get away. Anyway, for number 11, then, a box of Lego blocks contains 4 red blocks, 5 yellow blocks, and 3 blue blocks. How many ways can you construct a tower? What? Oh, this is an odd question. Can I construct a tower using all the blocks? Did you mean? Did you mean? Person who wrote the question, did you mean did you forget, did you a word? Right? Did you a word? Or did you a phrase, rather? Did you forget to say that you mean to use all the blocks? Because that's important. Right? Because right now we don't know, like, is a tower 2 blocks? Is a tower 3 blocks? If a tower can be any number of blocks, we have got a freaking massive question on our hands. Because we have to figure out how many ways they can make a 2 tower block, and then a 3, and then a 4, and then a 5, and then a 6. All the way up to, what is it, 12. So I'm not doing that. Right? Just not going to do that. What I'm going to do is assume the tower uses all 12 blocks. Right? So what we have is red, 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 red. 5 yellow. 1, 2, 3, 4, 5 yellows. 3 blue. Right? So, just like up above here, it's going to be 12 factorial, divide by, well, there's a 4 factorial, a 5 factorial, and a 3 factorial. Right? Assuming that all these different color blocks are identical. So that then is going to make 12 times 11 times 10 times 9 times 8 times 7 times 6. Divide by 4 times 3 times 2 times 3 times 2. This 3 times 2 can cancel there. This 4 and this 2 can cancel with that 8. This 3 can go in there and make that a 3. Then I can just go ahead and multiply those guys. 12 times 11 times 10 times 3 times 7. 27, 7, 20. There we go. That's how we go about doing 11A. Then 11B. 11B was one of the ones that I kind of wanted to do on this set, right? Because 11B is just how many ways can we do it if the 4 red blocks are on the top? Well, here now we have to have, right? So our tower is going to be red, 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 red. These ones are fixed, right? These ones aren't going to change. And then for the other blocks, we're going to have our 5 yellow, and then our 3 blue. Right? So those ones are fixed. They don't change. There's only one way to have those, and that's just to have them all up there on the top. That's it. Right? And these ones down here are now 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 factorial over 5 factorial, 3 factorial. That is it. Right? So it's going to be 8 times 7 times 6 over 3 times 2. 3 times 2 cancels with 6. It's just going to be 8 times 7, which is 56. So it's just going to be 56 ways now. Right? Because if those 4 red had to be on top, well, they're stuck there. Right? They can't move out of it. So they're not affecting the different number of permutations or combinations that we can have. Permutations in this case. Right? Because they're just fixed. They're just staying up there the whole time. Oh. My notes to myself down and under my on the piece of paper that I fixed to my desk. That piece of paper has become incredibly inaccurate, actually. I should remove that. Because every single day I've got to like reconfigure my camera. I don't know what the heck is going on with it, but at least I fixed the drivers so that I'm not getting those blue screen of deaths anymore, which is nice, right? Like it's nice to not have blue screen of death. As a computer nerd, right? Getting your heart always like it's a real like it's a visceral sort of reaction to a BSOD. Let me tell you, it's like I'm running like Windows XP Black or something over here, right? I don't know. Maybe some real tech nerds will tell me how Windows XP Black because the crowdsourcing is actually far more stable. I doubt it though. But you know, if you want to use Windows XP still, right? That's the way to do it. Anyway, all right, I want to do 12 and 13 before I was done. So this is math 3101A unit 2. So let's do question 12. 6 tickets available for an upcoming concert. Well, 12 men and 8 women have qualified to win the tickets. How many ways can the 6 lucky winners be selected from those who have qualified? You remember years ago, Twitch chat? You don't, because you're not real. Twitch chat is just a figment of my imagination. But also because you're not in St. John's, and you weren't in St. John's circa like 15 years ago. Remember when they had Win to Get In? They had a Win to Get In Queens of the Stone Age concert that you won tickets for through like buying Molson Canadian. Let me tell you, me and my buddy at the time bought we drank nothing but Molson the entire time that Win to Get In was on. Like it worked. I mean, they targeted that exact market, right? I wasn't even like crazy about going. I wanted to go, but like, you know, but my buddy was just Marty Kurt. He was just ravenous. Like he needed to go see that Quatsa concert, right? Are you supposed to call them Quatsa, or is that not what we do? But he really wanted to go, and he never won one. He didn't win one in the end, so he had to go on Kijiji and like buy a ticket off of somebody else who won, right? And the thing is, when he went, like that concert lives in infamy. You know, like someone throw a friggin' shoe at the front man, like they booed them off stage, and they were like getting hit and pelt with stuff from the audience. And it's like, this is Queens of the Stone Age. Like this is this is a legit band, like a fairly big band. And like they're coming to St. John's, Newfoundland for this one, big show that like lots of people really wanted to get to, and it turned into a real shitfest. But I mean, that's what you get, right? That's what you get, I guess, when the only way to get to that show was to drink a lot of beer. So you had people going who like weren't Queens of the Stone Age fans, who were just fans of Molson Canadian and won tickets to get in. You had fans who really wanted to go and would have had a great time there, who couldn't go because the only way to get tickets was to just win them randomly in Molson Canadian. Right? Like, boy, it really sounds like a recipe for disaster. And you know what? Queens of the Stone Age is never going to come back to Newfoundland. Not in a million years. Not after that. There will be a new Stone Age and new Queens of that age before a band of that name will ever come to St. John's again. And it's all because Labatt, or Molson, right? Why did I say Labatt? It's all because of Molson. And the brilliant idea that we would make Kurt drink a whole bunch of Molson Canadian instead of other beer so that he could fail to win a ticket and then have to buy one on Kijiji at a scalper rate and then go and see the worst show that there's ever been in the city. All right. I'm sorry, Calais. I should have warned you before that started that you could fast forward the video by a solid minute. I should have warned. Anyway, I just want to humor myself in talking about some stories, right? Because I'm an old man. I'm an old man who likes to talk about stories. I'm not old. I'm 37. I'm not 37, actually. I'm not even that old. I'm not even old enough to use that Monty Python quote yet. Couldn't just call you man. You could have called me Dennis. I didn't know you were called Dennis. Didn't bother to find out. Anyway, there's 6 tickets available. How many ways can 6 lucky winners be selected from those who have qualified? Well, 20C6. Come on, right? Like, you know what? You know what? I'm just gonna use this. We got there. 20C6. Look at that. We did it. We did it, Reddit. We made it. There we go. 12B. Oh my god. Just gassy today. Holy god. How many ways can the 6 tickets be awarded if at most 3 men can win? Oh boy. Okay, so now we got a bit of work. Okay. So I'm going to keep using the calculator for these ones because I've got a few steps. But at most 3 men can win. I mean, we can have 0 men, 0 mans, 1 mans, 2 mans, and 3 mans. Right? So I could kind of do the other way and then subtract from the total, but it's actually going to be the same amount of work either way. Right? So we either are going to have 20C0 times, sorry, not 20. How many men are there? 12. Right? Yes. So 12C0 times 8C6 plus, yes, 12C1 times 8C5 plus 12C2 times 8C4, right, plus 12C3 times 8C3. Yikes. We've got a few. We've got a few to get through here. Well, first up, I'm just going to go ahead and use a calculator, right? So 8C6 is going to be 28. So this is going to be a 28 over here because I know 12C0 is just 1. Anything C0 is 1, right? 12C1 I know to be 12. So then I'm going to do 8C5 and times that number by 12. So that's going to be 672, right, for the second term. And the third term is going to be 12C2 times 8C4, 4620. Then plus this last one over here, which is going to be 12C3 times, I open my brackets here just so I make sure that what I'm doing, that the calculator, calculates it correctly. Right? Follows the order of operations that I want it to be doing. So now I'm just going to add these guys together. Right. So it wasn't all that bad. It wasn't, but if we were to do all these out by hand, this would have been quite a bit of work, right? On a test or something like that, Calais, there won't be a question quite this big for you to do. We do expect it to be done by hand in a sense, just because we're not actually providing the calculators, especially via distance. We're not providing calculators that can do these functions, right? But at least on the test, your questions will be a bit shorter than these ones, so there won't be this much. Won't be this many sort of, NCRs that you had to do in the one question. How many ways can tickets be awarded if at least one of the winners must be female? Okay. Well, how am I going to solve this question? This is one of the reasons why I wanted to do these ones, was to get on to 12C here. If at least one of the winners must be female, boy oh boy. So at least one means it can be 1, it can be 2, it can be 3, it can be 4, it can be 5, or it can be 6. So that's, do I have to figure out 6 different cases and add all those together? Well, kind of yes, but actually no. Because what I can't, because I know the total number. I've got the total number over here, and this is, I know that whatever other number I find is always going to be less than this, because this is simply the maximum number of combinations that we can have. So if we need to have at least one of the winners must be female, well, that means what situation can't we have? Well, we can't have the situation where 0 of the winners are female. That's the only situation that we can't have. The rest of them are fine, right? So I'm going to figure out the situation that we can't have, and then I'm going to subtract it from the total. So the situation that we can't have is 12C6 times 8C0, which is the situation where 0 right? So this is the only case that we can't have. So then 12C6, I'm going to pluggerino, 12C6 here like that, 924, 8C0, well, I'll put it in here just to show you good faith. 8C0 is, of course, 1. Anything C0 is 1, right? So that's just going to be 924 cases we can't have. So then we're going to do the total, 38760, subtract 924. It's going to be 37,836. And there's our answer for C. A little bit quicker, a little bit quicker and more easily than what it would be if we had to figure out, the number of chances for 1 female, 2, 3, 4, 5, and 6, and then add all those together. We would get that number though, right? So we got there in the end. Okay, I was going to do question 13, so yes, let's do question 13, and then I think then we'll be at a good point to call it for today, I think. Right, so question 13 then. Used car lot has 7 new additions they want to place side by side along the front of the parking lot. 2 red, 3 blue, a black, and a green. How many ways can the cars be arranged? Right, well this is just the same as that Lego question from the previous page. Right? So there are 2 red, 3 blue. So I'm going to use Magic the Gathering notation again and call those U. 2 red, 3 blue, a black, and a green. Rubig. That's a tough mana cost. Look at that. R-U-U-B-G. Come on now. That better be a beast. That better be a beastly creature, let me tell you. I mean, not literally like creature type beast. That doesn't mean anything, really. Anyway, another digression. Simple, just for Peter. It's a digression. Nobody else in chat is like, why are you talking about Magic? It doesn't. You don't stream that. I don't. Not yet, anyway. I don't know. I don't know that MTGA is what I would stream. Although MTGA is like miles and miles and miles, like light years ahead of Modo. Oh my lord. What a program. What a program Modo is. Anyway. So how many ways can the cars be arranged? Well, there's 1, 2, 3, 4, 5, 6, 7. So 7 factorial, right? Because there's 7 in total. 2 red are the same. 3 blue are the same. Not super difficult stuff, is it? 7 times 6 times 5 times 4. Well, I mean, it's tricky before you know what to do, I suppose. But then after you know what to do, it's generally going to not be super hard, right? 7 times 6 times 5 times 2. 420. Hey, LeMayo. There we go. 420 different ways to rearrange those vehicles. So how many ways can you arrange the car so that there was a red car in the beginning and at the end? Well, now, right, we've got our 1, 2, 3, 4, 5, 6, 7. We've got our 7 spots, right? But we know there's going to have to be a red one here, and there's going to have to be a red one here. So then how many are left over? Well, what's left over is Ubg, Uber good, right? Now it's a 3 cost card. This you could maybe see this, but it'd be some beastly old like I don't know counterspell or something. 3 blue and then a black and a green. What a card. What a card that would be. Get at me if there's one of those. Like crypticist command. Jesus. 5 factorial, 3 factorial. Right? Because there's 5 things, 3 of them are the same. It's just going to be 5 times 4, and that's going to be 20. There we go. We got there. All right. That is the end of the questions that I wanted to do today. Kelly, I hope if you listen to all that rambling, just nonsensical banter, apologies. And you're a trooper. If you listen to all that, seriously, if you heard all the nonsense that I was saying, just you suffered through all that in order to hear me explain why this answer was 20, then like good on you. You're doing great. You're destined for good things in school if you're able to listen to me drone on like that just to get that answer. Boy, oh boy. Okay, well, that's another stream down. Okay. Yeah, thanks for being here with me. You know, stay safe out there, and yeah, I hope to see you all again tomorrow.